Good evening, everybody. Welcome along to Café Scientifique. My name is Scott McIndoe, and I am the host for the Chemistry Cafes. And tonight it's my great pleasure to be introducing my friend and colleague, Irina Paci. Irina was born and grew up in Romania before coming to North America to become educated at Queen's, and then went to the, more educated at Queen's, and then she moved to Northwestern before joining us at the University of Victoria 2007, and she's been with us ever since. Irina studies, like most chemists, studies molecules, and molecules are tough to study for all sorts of reasons. Part of the reason is that molecules, of course, are very, very small. And just to give you an indication of how small molecules are, I brought along a 3D print of a molecule. Does anyone know what molecule this one is? It's a buckyball. This table's onto it. This is a buckyball, but I have scaled it up by 8 orders of magnitude. So it is 100 million times bigger than it actually is. And to give you an idea of what that scale difference means, if you took the Earth and you scaled it down by 8 orders of magnitude, by 100 million times, I would have a globe in my hand about the same size of this buckyball. So we are to molecules as the planet is to us. And so studying molecules is really challenging. We need powerful tools to do it. And Irina's tools are largely computational, but also amazingly powerful. And she's going to tell you about that tonight. So please join with me in welcoming Irina to the Café Scientifique stage.
Thank you, Scott, for that introduction. Actually, I think you finished talking about models, so maybe what I have to say here is very little tonight, just about computers a little bit, and that's about it. No, actually, I'm going to talk to you a lot more about models and how scientists use models and think about models, and about theories in science and so on. It's a little bit of a mixture of telling you how we do chemistry on computers these days, and also a little bit of philosophy of science and how we think about models. That's what the talk is about today. But I'm going to start by asking you a question, and I promise it's not meant to be a controversial question, so don't take it controversially. Okay, it's not controversial. Not controversially. Do you believe in science? Okay, what do you mean by that? When you say yes, what do you expect science to tell you, to give you? You can take a minute to think about it, because this is a that means different things to most of us. The process, yes, of science, right? Doing science, of discovery, yeah. And what are you discovering? You're discovering truths, universal truths. The rational process, that's right. Nature, learning about nature, that's right. So those are the things that you expect science to give you, right? Some truths about nature, right? Okay, I have another question for you. What is truth? I told you that it's philosophy. You were hoping for science here, and you're getting philosophy. Yes, whatever version, yes. Beauty is truth. And we don't really know what truth is, right? Is there, I mean, scientists in general are pursuing this truth, right? Some sort of absolute reality that exists independent of us and just sitting there waiting to be discovered. But have we, like, you're expecting science to give you that, but we haven't reached it yet, right? We're still digging, we're still looking for it. Okay, and what truth means, it can be a little bit unclear, right? In court, for example, a truthful witness, somebody who tells their truth, might be presenting a misleading or false statement of facts because that truth, that witness's truth, has been processed through their experience, right? So it's maybe something they thought they saw, right? So science investigation and looking for the truth, for the absolute truth in science, it's very similar to that. We have the lenses that we have, and then we can investigate nature as well as we can. But what we see is the reality, the nature that we're discovering. It changes all the time as we discover more things about it, and that's why we still get paid to do the things we love. So that's okay. Okay, so we're doing these investigations in pursuit of truth, learning about nature. And the way we learn about nature is we're constructing these objects of mind in our minds. We're constructing theories about how nature works. We formulate hypotheses that we pursue in order to maybe develop those theories. And the topic of our talk today, we create models, okay, to represent what we found, okay? So that's part of the scientific process, okay? Building these objects of mind, we'd like to call them. Okay, that allow us to tell you how nature is organized and so on. Okay, in terms of the scientific process, there's this cartoon that's quite well known in the scientific community by a guy. His name is Randall Munro, and he draws the XKCD cartoons. And this cartoon, that's one of my most near and dear to my heart as a scientist, is this person finds a box with a lever on it, and the lever says pull, and the person goes and pulls on the lever and gets hit with a really, really strong zap, just like big zap, jumps back. And then the outcome of the experiment splits in two, where the normal person says, I guess I better not do that. And the scientist says, I wonder if it does this every time. That's sacrifice in the name of science. No, it's of course related to the requirement of reproducibility in science, right? Okay, I have another question for you. Speaking of rules, right? And just kind of, I wonder if it does that every time. Every time I pull the lever, that's a rule, right? It's going to zap me. Did you ever come up with a rule? Just from your experiences, maybe a statistical rule that you noticed, something like red apples are sweet. Did you come up with a rule like that? Of course you did. You can just tell me about it.
Well, if you're racing sailboats on English Bay, there's always a lift off Spanish banks.
Okay. I didn't understand that.
I'll go home now. There's a popular belief that if you're trying to win a sailboat race on Spanish banks, the wind will favor you if you head over on English Bay. The wind will favor you if you head over towards Spanish banks. So everybody does that and runs aground.
There you go. That's a rule. That's almost like a universal truth, it sounds to me, like, because everybody knows it. Right, yeah, yeah. Anybody else? Yeah? Or just a statistical truth. You've noticed that things happen sometimes.
I'm aware that I'm a conscious being.
Mm-hmm. Yeah.
And that's a truth.
That's a truth. That's a universal truth, right? We're all conscious beings. Yeah. So these are the sort of. Oh, Scott's got an example. I like that statistical truth. That's great. Where I was going with all this, and I'm not sure how many of these we're going to explain. Usually, when you discover something like this, especially a statistical truth, you're also looking for an explanation, right? Like red apples are sweet because they're ripe, and ripe apples are sweet. And the reason I want that explanation is because I really want to, to eat mainly sweet apples. So I want to develop these rules so that I can predict what's going to happen next time. So Scott, for sure, like yours, you don't need an explanation. You just need to bring your umbrella. All right, but do we have an explanation for the English Bay?
There probably is, but the sailors don't worry about it. They just follow.
Yeah, they just do it. Yeah, some truths you just follow. I think those are maybe the universal truths. That's probably the way it is. All right, so scientists have been trying to kind of grapple with this, the process, right? How do we do the scientific process? How does this work in general? What are good ways to pursue truth, right? And the investigation of truth in science. I have some quotes from various scientists along history. All right, Da Vinci says, no human inquiry can claim the status of true knowledge without passing through mathematical demonstration. It must be mathematical. And if you say that sciences which begin and end in the mind possess truth, this cannot be allowed, but must be denied for many reasons. And first of all, because experience does not enter into such mental exercises. And without experience, there is no certainty. So according to Da Vinci, I think all of our colleagues who are particle physicists would be like out of a job. Anything that's in the mind and cannot be mathematical. Okay, so somebody else, Auguste Comte, philosopher in the 19th century, had a problem with math and chemistry, actually. I'll tell you what he said. He said, every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational. He was pretty aggressive, and contrary to the spirit of chemistry. If mathematical analysis should ever hold a prominent place in chemistry, an aberration which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. Now, those are opinions. Strong opinions. All right. And then Louis Pasteur, who discovered bacteria and antibiotics, said the merit of a new theory does not rely on the fact that it is true. There are no true theories. Its merit depends on being fruitful. Okay, that's what Pasteur said, and he was paraphrased by the British statistician George Box into a quote that you may have heard before. All models are wrong, but some are useful. So I'll tell you about our wrong models. Okay, so what's the difference between, I talked about theories and hypotheses, and I talked about models, and I think this is my cue. Yeah, I'll give you one more page, Scott, and then you can distribute the models. Okay, so what's the difference between a theory and a model and a hypothesis? I mentioned hypotheses as well. So theories are constructs that bind together these rules that we discover that try to be truthful. and perhaps are truthful according to the knowledge at the time. A theory is really aiming to treat similarly both future understanding and past understanding. So theories are really meaning to be complete and truthful. Okay, they really try to do it. Looking back, looking in retrospective, most theories are false because as we uncover new things about science. You know, we find that the old theories don't hold water anymore. Or we discover that there are little things about the old theories that need to be added in. They need to be appended. So those are theories. They try to be truthful. Hypotheses are theories in development, baby theories. So hypotheses are not meant to be holding truth. They're meant to be amended, they're meant to be tested. Scientists usually formulate hypotheses and then they poke at them and investigate. They try to see if they can devise techniques that may prove them truthful or false in order to build a theory in the end. Okay? And models come from a Latin word that means image, examples, prototypes. Models are not trying to be truthful. That's the big difference between a model and a theory. Okay, a model actually tries to represent something, and Scott's gonna distribute some models around, some chemistry models. Okay, models try to treat some aspect of whatever phenomenon they're describing really well, and they do away with a lot of the other aspects. That's why it's called a model, okay? They try to teach you something, and it's a representation, if you want, a simplification that preserves some of the aspects of the phenomenon, but not all. Okay, so depending on where we are in the development of these theories, you can if you haven't studied or you're at the beginning of studying something, of a new phenomenon. Okay, you might first learn some facts, learn some things about your phenomenon, develop a model, create some hypotheses, and then from those hypotheses build theories. So they go in this direction. Or if you'd like to go the other way, you're not yet to put them together. Don't put them together yet. No building the models yet. Okay. Okay, we got to talk about the atoms first. Not the atoms, what the poles are. Okay? If you already have a theory, okay, about what you're studying, then perhaps you're basically building, you know the theory, but you build models like we do about molecules and atoms and things like that, right? And you build models to demonstrate certain aspects, to explain facts. Okay, so I do have a couple questions for you before I move on to those models, okay? And since we've been talking about models as representations, right, of things, have any of you, or how many of you, have used models in your professional works and work? And have you made decisions based on them? Can you tell me about them? Mm-hmm. Yeah, awesome. And you make decisions, right? Or at least you try to convince others to make decisions based on that, right? How about you? Computer utilization, right? So in a social science sort of, or actual computer utilization, okay. And did you make decisions based on those? Yeah, absolutely, okay. Do you, if you haven't, I'm not gonna ask my husband over there because I've heard about his models. All right. Even if you didn't, or even if you did use models in your professional lives, have you used models in your day-to-day life and made decisions based on them? Yeah.
Can you answer questions as you go, or do you want to wait till the end?
You answer my question first, and then I can answer yours.
Question about what you're saying is what I have to ask.
What am I saying?
Well, you're saying that you use models
Mm-hmm.
to make decisions, and that is not my understanding of
You can use a model to make decisions.
Can you give me a very simple example?
Weather forecasting. That's one example of a model. It's a model, right? So a weather forecaster has a model of how the weather comes about, right? How the clouds, how the masses move. I don't know enough about weather forecasting to actually stand here and tell you about it. But they run some computer codes, and then they say 30% chance of precipitations tomorrow, so you may or may not decide to bring your umbrella with you when you go to work, right? So you make a decision based on that. Okay? And that's a model, not a theory. Because a theory is a truth as far as we understand, right? Whereas nobody thinks that the models that meteorologists use are complete and truthful, right? So they're incomplete for sure. And even according to our understanding now, we completely know that those are not theories, right? Yeah. Any other models? Does that answers your question? And hopefully we can come up with other examples of models that people use to make decisions. Hydraulic models for water pressure. Yeah. Is there a hand up there?
I feel like you're in a whole different realm do it. So I was a paramedic for many years. When we were doing it, we always had to do models.
Mm-hmm.
At the beginning part of our lessons about what we were giving to people.
Right.
So we learn a lot about exactly what we're giving to people in terms of models.
Yep.
But you don't learn it on the full spec of what you guys are learning in terms of university.
So you just needed a really simple model, right?
Yeah.
Yeah.
So we do our, and to be fair, they got intense, right? You're modeling intense drugs.
Sure.
For us.
Yep.
But at the end of the day is we put together models.
Yeah. And you use them.
We really had no idea what we were.
Mm.
We're all paramedics.
Mm-hmm.
Right? And we're like, oh, whatever drug is, we'd model it, and then at the end of the day, but you also knew what you were putting into that, right?
Yep.
Yeah. But models were a big part of my college and university experience being a medic.
Yep. Yep.
I actually have another definition of models, and that's making an image of a certain part of a process.
That's right.
Makes it consumable,
Yeah.
but not necessarily the whole theory, but it's meant for consumption.
Meant for consumption. Like, let's say an architect makes a model, right? And then that gets built, right? That's another example of a model. Yes.
Models are used all the time, quite often in software development,
Mm-hmm.
where you would describe an object and then based on that model,
You just,
would
yeah.
expand. Yeah.
And yeah, you just capture a few things. That's right. Yeah. So those are all examples of models that we use in our professional life, we use in our day-to-day life, and we make decisions based on them. And they really are not meant to treat the full process, right? The full phenomenon. Okay. So I've left. Now you're allowed to open the baggies. All right. And you can take. I have my own baggie here. Okay. You get to take the biggest ball you can find in your bag. Okay, just the one. We'll put it all together. We'll play with Lego eventually. Okay, mine is red. I mean, they're the same size, but I just picked one. You got a red one? Perfect. A red one. There are some carbon, some black ones, gray ones. Oh, I'm giving it away. All right, what do you think that's a model for? An atom? Yeah, sure. It can be an atom. Okay. What else can it be a model for?
Are we doing hydrogen dioxide?
Yeah, eventually. Yeah. when we get to molecules, right now we're on atoms. Atoms. But this spherical object can also be, I don't know, it can be anything. It can be a model for a chicken. I actually have a chicken joke. Here's the chicken joke right here. A farmer noticed that his chickens were sick and called in a biologist, a chemist, and a physicist to investigate what was going on to diagnose the problem. The biologist observed the chickens, concluding, I can tell you there's something wrong with your chickens, but I don't know what's causing it. The chemist took fluid samples from the chickens back to his lab and then returned and said, I can tell you what's infecting your chickens, but I don't know how they got it. Meanwhile, the physicist was sitting on the floor, scribbling madly on a few pads of paper. Suddenly, he jumped up, exclaiming, I have an answer, but it only works for chickens for spherical chickens in a vacuum. So this could be a model for a spherical chicken. And if you had or a goose, actually, I was thinking geese eventually at the beginning, because I do have other chicken jokes later, but if you had a scale model of Swan Lake, let's say, I go around Swan Lake quite a bit. So if you had a scale model of Swan Lake, and one day it's like really, really packed with geese, and you considered spherical geese that were kind of to scale with Swan Lake, you can actually have a pretty good model of how many geese could pack Swan Lake on that day just by using spherical geese. So this could be a model for geese, but it's actually, you're right, it was really meant to be an atom when I put it in your baggie, because this is a chemistry modeling talk. Okay, so how truthful do you think? How truthful do you think this model for an atom is? Not great, right? It's not the best model for an atom, but it does some things, you know. It just kind of conveys that mine is an oxygen atom, because we know we color them red if they're oxygens usually. If it's white, we color hydrogen with white. Carbons are gray. Nitrogens are green or blue. Blue usually, blue. Chlorines are green. All right. You know, we even have colors assigned to our atoms. Do you think atoms actually have colors when they're in molecules? The oxygen is not red when it's in water. Okay, so we'll talk about what truthful models for atoms scientists have come up with. Okay, so I'm going to put this. I can keep this. Okay. So historically, even actually in ancient Greece, people thought that atoms are the smallest units of matter, right? And atoms were indivisible. Actually, that's what the word atom means, something that's indestructible. Okay, so but back then they thought that different elements had atoms that looked kind of different, had different structures. They thought maybe iron was a strong metal, you know, really good for building stuff. They thought maybe iron atoms had hooks that would kind of come up together and create this really nice strong structure. And it was only Dalton in like 1803, early 19th century, who came up with the idea that perhaps atoms are indestructible, sure, but they're spherical. And then he had some more ideas, like maybe all of the atoms of the same element look the same, okay? But for different elements, there are different, identical atoms, okay? Then let's see, who else came up with a better model for the atom? After Dalton, who actually also came up with the theory of how atoms combine to make molecules and compounds, okay? He also had the first chemical symbols for elements, which was kind of interesting, because nitrogen, in Dalton's chemical symbols, you know, now we write nitrogen like an N, right? But in Dalton's chemical symbols, it looked like the Mercedes-Benz symbol, and hydrogen was like a dot in a circle. And so he had pictograms for elements. Those were his names. I thought that was kind of cool. Okay, then Thomson found that atoms were not indivisible. This was late in the 19th century. He found these smaller particles, way smaller particles, that he could generate in cathode ray tubes, which some of us have seen cathode ray tubes. Do you know what, where some of us have seen CRT TVs, right? So we've used cathode ray tubes, and Thomson used the cathode ray tube to figure out that atoms actually were not indivisible. Okay, he found out about electrons, and he actually created the plum pudding model of the atom. Okay, so in the plum pudding model of the atom was formed of this. It was this spherical structure that was positively charged, and then the electrons were kind of stuck in there, like raisins in a plum pudding. Okay, so speaking of charges, I have some chicken jokes. Why did the chicken cross the road? Speaking of charges. Oh, why? You asked why. Okay, Charles Coulomb's perspective. The chicken found a similar chicken on this side of the road to be repellent. Scientists have the best chicken jokes. All right. No exaggeration here. Okay, so Rutherford did some experiments where he was firing these alpha particles, which are charged helium atoms, ions, okay? He was firing them at gold foil and found that some of them would be reflected. As far as he was concerned, gold foil was something that was, impenetrable. So he was firing these alpha particles at gold foil and found that some of them would be reflected pretty significantly, but some of them went right through. So he came up with this idea, this new model for the atom, that was that atoms were mainly empty space, that there was a nuclear charge that was positive, very small, and that the electrons were mainly orbiting the nucleus, but they were very small, and the atom was mainly empty space because of these experiments. Oh yeah, Rutherford has one chicken cross. Why did the chicken cross the road according to Rutherford? Why? Okay, I'll tell you why.
Too far to go around.
This one is a pretentious answer. You'd think that would be just forget the chicken, right? Okay, the differential cross section for forward chicken scattering is quite large, so the chicken will most likely cross the road if it was initially heading in that direction. I didn't understand that one, so it's okay. It's okay. Okay, but this still doesn't explain why the negatively charged ions aren't crashing in the nucleus, right? So we haven't developed a good model for our atom yet, okay? And then it kind of got to be the early 20th century, and Bohr came up with this, the quantum theory of atoms, of particles was just developing then. So Bohr came up with this idea that perhaps the electrons are orbiting the nucleus at specific energies. So they couldn't have any distance or any energy away from the nucleus, but they had to be at specific energy. This was coming from the quantization ideas of the quantum mechanics that was just being developed. This is called the planetary model, right, where each electron has like a different orbit around the nucleus. Okay, this was Bohr's model of the atom, and I have another chicken cross the road. You can throw your napkins if you had enough. I only have 2 more. Okay, but it's not according to Bohr; it's according to de Broglie. Interesting. It always seems to flap its wing an integral number of times before it comes back. Okay. They're terrible. Okay, no, they're fun. Come on. All right, so finally, Schrödinger postulated the electrons actually don't behave like particles orbiting the nucleus, and this is where quantum theory is just completely mind-bending. But they behave like waves. The electrons are waves around the nuclei. And you can never pinpoint where an electron is. You're actually you might be able to, by describing this wave-like nature of the electrons, you might be able to tell of regions of space around the nucleus where the electrons might be, but you can never actually say the electron is over there, okay? That's the wave theory of the electrons in atoms. And it's according to Schrödinger. And Schrödinger actually did another nice thing, and he wrote down an equation for electrons and atoms and particles that behave like waves. Everything behaves like waves. This tool over here is you can't notice it, but it's a wave. Okay, it just has a very, very small wavelength. So Schrödinger actually came up with the Schrödinger equation that gives us a mathematical model that has actually become, it stood the test of time and of tests and experiments long enough that it's become a theory, the quantum theory of atoms, and it gives us a mathematical description for the way electrons behave in atoms, and when we make molecules, for the way electrons behave in molecules. And I have the last chicken joke. All right here. Why did the chicken cross the road? Schrödinger. The chicken doesn't cross the road. Rather, it exists simultaneously on both sides. Just don't measure it. So wildly enough, these ideas of quantum behavior have been actually verified experimentally. And there are these cool experiments that were done by Alain Aspect in France. He's been working on this since the 70s, and he got the Nobel Prize just last year in 2022 for his work in quantum information science. So he's moved on from measuring entanglement of photons and whether photons self-interact and electrons experience self-interaction, which would be something that would happen if electrons behave as waves. But yes, his group have done these amazing experiments that have basically confirmed Schrödinger's theory, and the others. There were many scientists, not just one scientist came up with this cool idea of wave behavior of matter. But there have been many experiments that verify these theories to date. All right. So now that you've been paying so much attention to me and you've been talking to me, and that's really, really great, I get to have you do an activity. And then this activity, we're going to get to put our molecules together. Okay, so you must use all your bonds. You must use all the bonding spots on your atoms. Okay, and I have a molecule here as well, and then we'll talk about the molecules. Yeah, you only got one molecule. Yeah, so you stick the bonds in the holes. All right. Oh no, my carbon is not the right carbon. Okay, I don't have a bond. Okay, this will work. How's it working? How's it going? Do you have a big one? Oh, you made a molecule. Awesome. Yes. Very good. It's the Mickey Mouse molecule. Also known as water. Okay, so you've got a molecule. I've got carbon monoxide. Scott, what do you have there? Chloroform, very nice. Well, maybe not nice. I don't know. All right, what do you have? Water? Oh, nice. What do you have? Clean. And what else do you have? Oh, that's chloroform as well. Yeah. Yeah, very good, very good. So it's got 3 chlorines, a carbon, and a hydrogen. Yeah. That's formaldehyde. What do you have? Ammonia, very good. Yes. I can't see what that is. It's something with a lot of ground. Oh, I think maybe that's phosgene or something. Just with the wrong color atoms on it. Yeah, I bet it's phosgene. All right, I ran out of atoms of the right colors. That's what happened there. Some people have carbon dioxide, right? Some people have water. You've just each made your molecule, okay? In this model, right? Okay, all right. So what's a molecule? It's a combination of atoms, but you stuck them together somehow. Bonded atoms, okay. So what are bonds? Yeah, they're attractive forces between atoms if you want, but they come from the fact that those atoms actually shared some electrons. Okay, so you can think of it as when you bring the atoms together, if they have some sort of affinity to one another, they share some electrons and form some bonds. Or the way I like to think about it is we have these molecules, they have some nuclei, they have some electrons, and the electrons couldn't care less about what atom they were coming from. They actually are electrons who are existing in this new molecule they're in. They're the water electrons. They're not the hydrogen and the oxygen electrons. They're the water electrons. And the water molecule behaves the way it behaves because its electrons behave the way they behave. Okay? That's the model for molecules. And the nice thing that Schrödinger did is that he laid out those equations. So now we have mathematical descriptions of the way electrons behave in molecules. So it turns out that some electrons just like to hang out right by the nuclei that they came from, if you want. But some electrons just kind of zoom around, or they behave like waves in the space between those nuclei. They form the bonds. Okay, and some electrons like to do that for, in a benzene molecule, you have electrons that are shared between all 6 carbon atoms. Okay, so they can span quite a space, and similarly to benzene, if you have a graphene layer, right? Graphene, just a single sheet of graphite. It's a really cool material. In a graphene layer, the electrons can be, anywhere along the plane. They're fully delocalized along the plane of graphene. Same thing in metals, right? So they're really, really shared with one another. Yeah, as I said, they don't really remember what nucleus they came from. Okay? That's a model of a molecule. This is a model of a molecule. What I just told you is a model of a molecule. Okay, and we also have these Schrödinger and quantum theories that provide us with some mathematical background that we actually have to approximate. So we have to make models in order to calculate the properties of molecules on computers. But we have some math to do it, so that's really nice. And they take us pretty close to the behavior of molecules. So we're kind of going towards modeling in chemistry, right? We're already kind of there, and I'm getting to computer models. I have another citation here, a cited announcement from Mulliken, when he gave his Nobel Prize lecture in 1966. Now in 1969, well, I'll tell you first what Mulliken said. Okay, he said that the era of computing chemists, when hundreds, if not thousands of chemists will go to the computing machines instead of the laboratory for increasingly many facets of information, is already at hand, okay? So this was 66. In 69, people used computers to plot the trajectory of the moon so they could send people to the moon. It took a while, right, before computers could be used for anything more exciting than plotting. It's not very difficult to plot the trajectory. It's rocket science, but rocket science is not that hard. All right, so, but these days, we have these huge computers. We have thousands of computers, tens of thousands of computers sitting together in some room, using up a lot of electricity, making a lot of noise, but able to run calculations for us. So we can really develop approximations to Schrodinger's equations for all kinds of molecules and chemical reactions and materials, and we can use them to predict the behavior of molecules and materials, and try to develop new molecules and materials. They make better drugs, better materials for new computers, and so on. Sorry? No. Okay. So I'll tell you about some applications in the industry, for example, where people are using computers, and doing chemistry on computers. And it's really become, just like Mulliken said, pretty much every chemical company has a division of computational chemists who are simulating and trying to understand the behavior of whatever they're studying on computers. So drug development, all drug companies, you know, Pfizer, for example, has a division of computational chemistry where they test various drug targets. Okay, Pfizer is, we know them now because they gave us vaccines. Okay, but they test drug targets for how well they fit in protein binding sites, and they screen a lot of these drug targets, and the best ones, according to the computation, get taken up and taken to synthesis and then put through tests, and then there are many, many, many elimination processes before any drug comes to market. Okay? Development of activity or reactivity structure models, where people in various other chemical companies like Merck, let's say, companies that make other things than drugs, but even drugs, they can simulate parts of the molecule and try to understand what the relationships of the different parts of the molecules with their activity in a chemical reaction is. And people are simulating materials in the same way. IBM and Intel develop new materials for chips all the time. And everything sort of starts with computation, or if they have some materials that they're studying and they don't understand why they behave that way, they can use computation to try to figure out what's going on. Okay. So every time we do a new, we try to learn new things about materials and molecules with computation, and the next time we develop a new theory, we have to test it, we have to validate it, right? So that's what is generally done in academic research, okay? And companies usually use what we find to apply it directly to their products. Okay. I actually have, I mean, you thought you came here and you had dinner and a beer and listened to a free talk, but that's not the way it goes. I'm a prof at UVic, and so I have homework for you. Okay, you don't have to do, you don't have to do it, but if you'd like to, okay, if you'd like to, you could go home, okay, and I'm assuming quite a few of you have a smartphone. And on your smartphone, you can download an app that's called Webmo. Okay, Webmo. Web as in web, the World Wide Web, and MO as in molecular orbitals. Webmo. It's right there. You can download it if you'd like, right on your phone right now if you get onto the Herman's Jazz Club Wi-Fi. And in Webmo, you could make your molecule, the one you just made the model of. You can make a better model of it, okay? You can actually calculate some of its properties. You can calculate and then display where the electrons like to be. You can calculate and display its vibrational spectrum. And you think that this is something easy to do, right? It's fairly, it's a basic computation, but if you think about your water molecule, the way the electrons are distributed and polarized and push each other around inside that water molecule is super important for the stability of water as a liquid, for the stability of saline water in the ocean. Very important for the reason why ice floats in the wintertime on top of lakes and oceans, and it doesn't sink. It's all described right there by that electronic structure that you can calculate on WebMO for your molecule, okay? Some of you had carbon dioxide. You know carbon dioxide is a greenhouse gas, okay? If you look at its vibrational structure on WebMO, you can actually see some of the modes of vibrations of carbon dioxide, and it so happens that when infrared light from the sun hits the carbon dioxide molecules in the atmosphere, it starts some of those vibrations, it excites some of those vibrations, they start getting going, and that retention of that energy from the sun is what causes the behavior of carbon dioxide as a greenhouse gas. Some of you had methane, same thing, okay? So you can really learn with electronic structure about the properties of these molecules. Okay, I'm out of time basically, but I got to tell you really quickly about a couple of big developments that are coming up in chemistry modeling. And one of them is, have you heard of machine learning? Who's heard of machine learning? Yeah, quite a few of you have heard of machine learning, right? Did you hear about ChatGPT? It's pretty fun. Have you tried to use it? You can have conversations. Yeah. So machine learning is some sort of artificial intelligence where you can train computers to utilize massive amounts of data and then learn about the phenomenon you're interested in and hopefully predict how other things are going to behave based on what they've learned from the massive data, okay? So you can basically bypass, scientists are hoping that eventually they'll be able to bypass solving Schrödinger's equation, as I told you, to learn about molecules, but instead train computers to solve these sorts of things much more quickly. Just sort of say, well, I've seen this 10 billion times, I know this number is going to be 3. Just like your doctor is going to say, when I've seen this 10 billion times, your ingrown toenail will be solved in 3 weeks by itself. Same thing with machine learning, but this is happening with a lot more data, and the computer is giving you that sort of information right away. It doesn't have to study it for a long time. Okay, that's machine learning. The problem with machine learning is that a lot of the time there's a bias in the data, so the data needs to be really curated and so on. And then the other thing is that machine learning models don't have in them any sort of information about why your ingrown toenail is going to solve itself by itself. There's no information about why they came up with that result. So you're not really learning as much as you do by actually studying things carefully. And I have an example of the perils of a biased data set, and I'm sure you've encountered it many times, right? The election polls, right? There's the example, but I have an example of that's from November 3, 1948, when the Chicago Tribune declared Dewey defeats Truman based on projecting results from the previous day's US presidential election. So they actually did exit polls by calling people up. Okay, and it turns out that, of course, Truman defeated Dewey by 303, votes to 189, so significantly in the Electoral College. The source of the error was that they were calling people in 1948, so who were they calling? They were calling those rich people who were more likely to vote Republican. Okay. Similarly, when scientists investigate materials, for example, right now, the data might be biased towards materials that are popular now, right? So that's part of the problem. Okay, so that's machine learning, and another cool sort of tangential development is automating both computation with machine learning and kind of tying it in with high throughput experimentation. There's a few initiatives that go in that direction that are looking really, really cool right now with a feedback loop where you can perfect your experiment by doing a bit of computation at the same time. Okay, and I promised in the abstract that I was going to talk about quantum computing, so you get 2 minutes about quantum computing. Who's heard about quantum computing? Everybody's heard about quantum computing. Okay, so quantum computers, this is another up-and-coming new way of doing. A qubit is like a quantum atom, basically. And a qubit can also have these values of 0 and 1, but it can actually be in a superposition of both 0 and 1, which is kind of interesting. So it can, on average, if you measured one of these qubits many times, you could get, you can get zeros and one and zeros and ones and zeros and ones and when you average it, you could get any value between 0 and 1. Okay. So at any given time, they're in both of these positions, right? And both 0 and 1. That's the crazy thing about quantum. All right, so I have some examples here, and then because when you're measuring, the wave function collapses onto either 0 and 1, a single qubit is not that useful. It's not that different from a regular bit that you're only going to read as 0 or 1. But if you have 2 qubits working together on a problem, it turns out that 2 qubits can actually have more values than just zeros and 1. They can be 0, 0, they can be 0, 1, they can be 1, 0, or 1, 1. Okay, and then if you have more and more qubits, you can have more and more, if working together, okay, you can have more and more values, and it goes as 2 to the number of qubits. Okay, so you can really do computation, whereas bits are independent, right? Qubits are entangled, so they work together, so they give you all these other options that they could have. And you actually have to completely rewrite and rethink the way you write software for machines if you're using these qubits with these crazy superpositions, but you can do a lot more computations with a lot fewer qubits this way. Because the number of operations goes as 2 to the n. Okay, so if you had 10 qubits, where do I have it? 10 qubits, then the overall system can be in 2 to the 10 states, which is 1,024 states. And the Google quantum computer that demonstrated quantum supremacy over classical computers was reported to have 53 qubits. Okay. So it was capable of being in 9 times 10 to the 15 states concurrently, a huge number of states. The problem is that no current quantum computer has been able to keep this entanglement of qubits. Okay, so right now, quantum computers are really noisy because qubits, they kind of like to stick together and know about one another, but then they just kind of lose coherence and they're no longer entangled. So there's a lot of noise, but there are quite a few technologies that are up and coming and creating new quantum computers. And definitely more and more qubits seem to be working together, every year when you read the statistics. And also right now scientists are working with developing software for these noisy quantum computers in order to try to take advantage of them. So hopefully, in the future, we'll be able to use these computers for all kinds of problem solving, including machine optimization problems like ship loading, chemistry, and so on. Okay, that's all I had to say. I'm happy to entertain questions, and thank you for playing along.
Awesome, thank you, Irina. Of all the things I was expecting to learn tonight, I wasn't expecting to learn that rocket science is not rocket science.
Rocket science.
So, do we have any, Irina's been kind enough to answer questions as we've gone along, but does anyone have any questions? Yes, over here.
My physics and chemistry training is only as good as public school. And so we all learned Bohr's model of the atom in public school, or at least we did here. So can you help me visually conceptualize, you know?
Sorry, finish your question.
What the predominant theory is about what an atom actually is. If it's actually how, you know, what the model looks like.
Yeah. So
Irina, just let me repeat the question. So
yes, do you want to repeat the question,
Yeah,
or should
yeah.
I repeat? Okay, go ahead.
I can do it.
Yeah,
So
go ahead.
the question is how would you, so the Bohr models are like this old-fashioned model of the atom. How could you best conceptualize and visualize a modern picture of an atom?
So there's the nucleus, and that's only because I'm a chemist. If you ask a physicist, they'll tell you a whole bunch of stuff about the nucleus as well. The nucleus isn't just the nucleus. There's a bunch of particles in there. But I'm a chemist. My nuclei just kind of, unless I'm doing nuclear chemistry, my nuclei just kind of stick together. And then the electrons, I told you, they're waves. They're not electrons. You cannot see an electron as a little point, okay? They're spread around. They're like a fuzzy cloud around the nucleus, and then different electrons occupy different fuzzy clouds, okay? So the lowest energy electrons tend to spend most time closest to the nucleus, and then there are other electrons that spend time a little bit further away, and the sort of clouds they make are shaped like the orbitals that you might have seen in before, where there are some s orbitals that are spherical, and then but these are also models that we solve by solving Schrödinger's equation for the hydrogen atom, and then we say all the other atoms must be the same, okay? So they're just models, okay? But yeah, you can't pinpoint an electron ever. And then in a molecule, you know, you have the electrons that are, you know, the lower energy ones that are sticking close to their nuclei, and then you have these electrons that are spread around the molecule, okay? In these clouds that are kind of, they can look, have you seen the bean in Chicago? You know, some delocalized electron clouds, orbitals, kind of look like the bean, just on top and on the bottom. And those are just the regions of probability of finding an electron, okay? And the atom never ends as well, because there's a non-zero probability that an atom from that table, an electron from that table is here right next to me. Yeah.
Yes, please.
I may not have this correct, but I understand that a water molecule, if you cool it, will lose its volume and weight until plus 4 degrees Celsius, and then you cool it more, it expands.
That's right. So
Hence how you floats on top of water.
yeah, right. So that's a really cool aspect of water that has so many repercussions on the way the world works, right? It's amazing. So it's not a single molecule, right? It's more water molecules. It's always more water molecules. And when they cool, they pack together, right, in different ways. So it so happens that their packing, when you're really close to 4 degrees, their packing in liquid phase is more compact than the way they pack in that ice that's forming right then at around 0 degrees. So So because of that, because the structure of water has a density maximum, so the water is most compact at 4 degrees, okay, that is, and then it gets to be less compact. When it packs together, the water molecules, the oxygens like to interact with the hydrogens from the other atoms, and they form these networks of ice, okay, that are really nicely organized, because that's why it's a crystal. And those crystals are lower in density than liquid water, 4 degrees, and that's why ice floats. Yeah, it's all about packing. Yeah.
Yes.
I'm curious about your experience with ChatGPT. We were actually talking about this on the way here tonight. I have tried asking ChatGPT questions that I know the answers to, and specifically, why is oxygen paramagnetic? And it gets the wrong answers. And I'm curious what your experience might have been with things like that.
So the question is why is ChatGPT so stupid?
Oh, you want the why?
And is there hope for improvement? Let me just expand on that slightly, because after I got the wrong answer, I submitted again, no, that's not right. And they were wrong about caring about the alignment of unpaired spins. And I got an answer saying, oh, I'm sorry for my mistake, you're correct, blah, blah. How does it know I'm correct? Right?
See,
And will that correction get built into subsequent inquiries of the same type?
I don't know if it will get built in. So ChatGPT is a text generator, right? It doesn't. It's not like a, it's not an encyclopedia, right? Its purpose is different. People will use it that way, right? What I found about ChatGPT, because you asked me what I found about ChatGPT, I think it's just the best BS generator you could possibly have, right? So if you're preparing a political speech, like, oh man, I think you can do really well with ChatGPT, but I know, for science, it just brushes everything. Really, it's really vague. It never gets into details, and I've actually heard colleagues say that if you ask for some citations, give me some citations for that nonsense you just gave me. It just creates citations. It just makes citations up. Yeah. So that's, for me, that's the it's what was it trained to do, right? What training set did it have, right? It's not really meant to explain science. Right? It wasn't built to explain science. It was built to create language, right? To create text. And that's my understanding. So it was trained based on how people write text, not on, all of the scientific literature in order to generate, correct scientific answers. Does that answer your question?
Yeah, it does. And
Yeah.
I think that it seemed to me that that's an indication that when you ask a scientific questions to which you actually know the right answers, it doesn't.
You could
it's not
possibly
very-
train it.
It's
Yeah.
not very encouraging in terms of asking it questions that you don't necessarily know the right answers to, where there's no agreement.
Yeah.
Yeah. Did you have a question?
Yeah, actually, you say that electrons here and there, and talking about BS generators. How do we get the electron then to predictably hit the spot where the CRT screen, if it's there and here?
Oh, because
So how can we focus an electron if we don't ever know where it is? How do we get a picture on our TV screen?
yeah, that's a great question. Well, if you get enough electrons kind of going and accelerating them, right? They're negatively charged. So if you accelerate them with a positive charge, you can get them to predictably move in one direction, but still as a wave. Right? So the image is created as a wave superposition, not from independent points. Okay? So the electrons are actually interfering with one another and creating those patterns that you see. They're not just hitting. They're not, points on the screen.
Most of them are behaving themselves.
Yeah.
Yeah, the back there.
So if electrons are a wave and they can be at any point, how can we definitively count them on a single atom? How do we know how many there are? I understand that the charge can be positive or negative, and then if there's an imbalance, you will see that in the charge.
Mm-hmm.
How do we know the number of them if they're just such a vague thing?
Yeah.
How
So
can we count electrons?
how do we count electrons? Oh man, these are hard questions. So in general, people do spectroscopy experiments. So you can promote electrons into other orbitals and measure, basically measure the energy that they absorbed in order that the atom absorbed in order to promote those electrons. So based on those spectra that you can get, you can actually figure out how many electrons. Is that right, Scott?
I mean, it's a complicated question.
Yeah.
No, that's a good one.
Yeah.
Okay, it is 10 after 7 now, so I'm going to wrap it up now. But if anyone has any questions for Irina afterwards, they're welcome to approach her and chat to her. And thank you all for coming, and see you next time.
Thank you.
Can we have our models?